but I haven't had a time today to do that. So I am recording this lesson. We are doing a new section. So we're not going to be using WebAssign for our assignments for the next couple of things. We're going to be using some PDFs that we as teachers put together for you guys from a couple of different sources. Oh my gosh, I'm like all sorts of whack here. Sorry about that. Okay, so let's get started and let's take a look at what we're doing today. And again, if you guys have questions, just go ahead and let me know. So we got 60321, right? And we're talking about parametric equations. So what we're going to do for the remainder of the semester is we're going to first take a look at linear and quadratic. And then next week we're going to add in circular. And circular is really where we use parametric equations a lot more. But you're going to see that we can do some really cool stuff with quadratics with parametrics. And so I'm pretty excited to do that. So what the heck is a parametric equation? Okay, so let's talk about that. What is a parametric equation? And what's cool is you guys have thought of equations the same way since your start of math. And that is you have an input and then something's happening with that input and then you get an output. But parametric equations looks at it a little bit different. And it considers, instead of input output, it talks about like variables, right? So what a parametric equation does is it takes variables. So it allows us to model things. Just a second. Sorry, I written down this thing I wanted to write down. So it allows us to model things when the variables, I'm just gonna say when the variables both change, or I should say all change, right? Because you can have more than two. So all change with respect to the same thing. Okay, and then I'm going to put a colon there. So we're going to have it. So a parametric equation allows us to model things when the variables all change with respect to the same thing. So this could be like time or rotation. Right, which is an angle. Okay, so that's what a parametric equation is. It's going to allow us to model things a little differently, and we're going to be able to get things different information than what we would with just like a basic input output. Okay, and what it's going to do is it's going to isolate the variables so that we can take a look at each variable independently and see what that variable is doing. And that's just going to tell us so much, right? So there's lots of examples of when we'd want to do this, right? So just think, anytime that you're interested in each variable of an equation and you want to see how it's changing, for example, like over time. So some specific examples of parametric equations would be movement in circular motion. So that's really big. Like anytime you have circular things move, so like that's the way that machines work. It's the way, like tires work. So anything that's rotating, it's polar coordinates. So we're not going to get the polar coordinates in this class, but if you guys take further math classes, eventually you're going to come up with polar coordinates. So you guys know Cartesian coordinates, right? Which is on the XY plane. A polar coordinate has to do with a 360-degree plane, right? So doing that. And then also, and this is we're gonna do a little bit of this today, is classical mechanics. Now you might have heard classical mechanics before, but you guys just learned that as high school physics or Newtonian physics is, right? So classical mechanics is just like the basic Newtonian law of physics, uses parametrics a lot. Okay, and the reason why it's called classical is because classical mechanics was done before really calculus and all of that, and so yeah, you can get into modern physics, which gets into like atoms and nuclear energy, right? Radioactivity, right on the micro scale. All right, cool. So we're going to take a look at parametrics today, what this means, what this looks like. You're going to find linear to be really boring because it is really boring. But luckily, most things that are interesting in life aren't linear. But it's good to start with linear things to do that, okay? Okay, so let's do this. Let's get into this. What is a parametric equation? What we're going to be doing with this, etc., etc. Sorry, I got a lot of windows open, so I just gotta. All right, so first is how do we go from, so if I have y equals negative 4x plus 7, right? So this is a standard, right, input output equation, right? So we're going to convert this to a parametric equation. Okay, so that's the first thing we're going to do. We're going to go from a linear equation to a parametric equation. And to do this, right, what are our variables? Our variables are our y and our x. So what we're going to want to do is we're going to want to find another variable that these two variables have in common. So the most common one, and the one that we're going to really focus on in this class, is time. So you can now, if it kind of helps to think of physics in this sense, think of an x and y axis, right? So the x is here, the y is here. So what we're going to do now, when you think of a graph like this, you think of it as my input changes, what happens to my y. But what a parametric equation says, as time changes, what happens to my x and y. Okay. So now, to do this conversion to a parametric equation, we're going to do something that you guys have seen before with composition, right? So we're going to remember you guys doing something like h of g of k of x, right? See how it's composition. Do you guys remember doing problems like that, right? So I think we did that first trimester pre-calc, right? And then we had this thing where like, well, how do you write it as a composition? That's basically what parametric equation is. Now, always the most basic way to convert to a parametric equation is just by making x equal t. Okay. So then that would mean then that y would just be negative 4t plus 7. Notice how both variables are in terms of t. Okay, so notice how both variables are in terms of t. Now, I'm not trying to claim this is our only solution for this, right? We can write a whole bunch of this in a whole bunch of different ways. So, for example, I could write x as 2t, but then I'm going to have to rewrite this to be the equivalent, right? So if I plug in 2t here, right, then this would have to be negative. This would have to be negative 2, right? Do you guys see how that would work, right? So I could make x equal any sort of t, right? Because all this is saying is that as time progresses, x goes with it. So that's basically saying this is time, right? Okay, and then if we look down here at the bottom, right, I don't know what that means. Sorry, just commenting on a comment. And then so we go here. Now, what this allows us to do is now we can focus on, we can say, hey, what's happening to the output as time progresses? What's happening to the x as time progresses? Now, this is a really boring example, and you're kind of like, why would you do this, right? So again, we're just getting introduced to this, and then let me show you where we go from here. So we can always, to get back, so to get back to a linear, we're going to solve for t in all equations, and then set the two equations equal. Okay, so that's how we're going to get back. And this is what I mean by it. Well, if we take a look at this top one, x is already in terms of t. So I'm going to take this next one and solve for t. So I get y minus 7 equals negative 4t. And then I get y minus 7 divided by negative 4 equals t. Okay, do you guys see how we have like a system? Okay. So notice how I have y minus 7 over negative 4 equals t and x equals t. So I'm going to set them equal to each other. Okay, so if I set them equal, I get y minus 7 over negative 4 equals x. Okay, and then my last step here is going to be solve for y. So I do that. I multiply both sides by negative 4. So I get y minus 7 equals negative 4x. And then I add 7. And I get y equals negative 4x plus 7. Okay. So again, pretty dang boring. And you're like, why are we doing this, right? It's kind of out of context. But if we don't understand the relationship between a parametric and a linear, then it's going to be confusing what we're doing. So a parametric isn't something different. It is looking at the same thing from a different perspective. And it's going to tell us different things. So it's a different way of doing it. And one way to think of it is you're going to get the where and the when rather than input and output. Okay, so that's what parametric does. So rather than saying, okay, I have input, output, we're really focusing on where do things happen, when do things happen, right? When time is 6, what's my x coordinate and my y coordinate, okay? So imagine like you were mapping something, right? And you're like, okay, it's been an hour. What's the x, y coordinate on this sphere? Okay, that would be really important if you were tracking something, right? You wouldn't be like, well, I have an input and an output, right? You'd want the x and the y. And that's what this is going. And it really breaks it down so that at the same time, we can independently solve for the x position by itself. We can independently solve for the y position by itself, or we can do both. Okay. All right. So that's kind of my intro there. And you guys, if you have questions, feel free to ask at any time. So we're gonna keep chug-a-lugging here. Okay. So that's my example again, going from a linear to parametric. Okay. Oh man, this paper's thin. All right, so our next thing that we're going to talk about, and we're going to be working on this tomorrow, right, in class. So the next thing we're going to work on is I'm going to have a parametric equation. So I'm going to have x equals negative 5 plus 4t. And then I'm going to have y equals 2 minus 3t. So, right, this is a parametric equation, right? It's in two different parts. It has the x in terms of t. It has the y in terms of t. So a parametric equation is just another way of describing the same thing that a linear equation would look at. So again, a parametric equation is just allows us to model things when the variables all change with respect to the same thing. So, right? So this is input, output. This right here is the exact same thing, and I tried to prove that to you, right? This right here, this parametric equation, right? X equals t, y equals negative 4t plus 7, right? That is the exact same thing as y equals negative 4x plus 7. So a parametric equation is just a different way of modeling something that you guys have modeled since Algebra 1, right? So this is just a line, right? Y equals negative 4x plus 7, right? That's y equals mx plus b. That's just a way to graph a line. Well, this is another way to graph that line, right? Now, think about this. Like, so what's the usefulness? Well, if you just wanted points, right, this wouldn't be the best way of doing it, right? Because you'd have to plug in t to get x, and you'd have to plug in t to get y. They're not together, right? Whereas here, x is your input, right? X changes with time. Whereas here, this allows us to change, x can change differently with time than y can change differently. So again, with linear, right, I knew you guys would be like, what gives, right? Like this doesn't make sense to use. You're right. With linear, it doesn't make sense to use unless you start out with it. Okay, and I'll do a couple examples with that. So yeah, you can't just use x and y. They're together. You got to use them both. They're both together describing the same thing. So, and that's kind of what a parametric does. It takes the one thing and breaks it into individual pieces so that you can get different information. Okay. So, for example, here, right, we have a parametric equation. Okay. But what we're going to do is we're going to change this to a linear one. Okay, so we're gonna start with parametric and we're gonna convert it to linear. Now, why would we want to do that? Because graphing the linear is really easy. And if you think back, that's mostly what you guys did, right? You were like, you practice graphing, you practice finding roots, you practice right from graphs, you practice finding y-intercepts, x-intercepts, right? Vertices. Okay, so that's what you guys spend a lot of time on. But I'm going to show you guys today with quadratics. It's really useful. So again, with linear equations, it's not that useful unless you start out with it. And we'll do an example of that in just a second, okay? Okay, so with here, again, the first thing I'm going to do is I'm going to solve both of these for t. So I'm going to use red for x. I'm going to use blue for y. So for x, I'm going to start by adding 5 to both sides and then dividing by 4. So I get x plus 5 divided by 4 equals t. And then here, I'm going to start by subtracting 2. So I get y minus 2 equals negative 3t. And then I'm going to divide by negative 3. And so I get y minus 2 divided by negative 3 equals t. Okay, so I just solved everything solved all for t, because that's what they have in common. And what that's going to allow us to do is it's going to allow us to do the chain rule, or you guys probably know it as substitution, right? We're going to chain them together. So I'm going to get x plus 5 divided by 4 equals y minus 2 divided by negative 3. So if I want to get this into a linear equation, I'm going to go ahead and solve for y. Right? I'm going to solve for y. And I hope you guys are taking good notes. I am recording this and putting this onto YouTube, but your book does a really terrible job of these. It's kind of like a system of equations. You can think of it like that, right? But a system of equations is a little bit different, right? Because a system of equations is like a system of linear equations or a system of quadratic, and you're still looking at x and y as input and output. Whereas this is a little bit different because this is looking at x changing with respects to time, and this is looking at y with respects to time, right? So like we're looking at them how they change respect to a different variable, whereas a system is just looking at x and y. So it is a little bit different, and that's why they're called parametrics instead of a system. Okay. So to solve this, I'm going to start by multiplying by -3. So I get negative 3x minus 15 over 4 equals y minus 2. And then I'm going to add 2. So we can break this up. So I can have negative 3x over 4ths, and then minus 15 over 4 plus 2 equals y. So the reason I did that is I'm going to multiply by 4 over 4. So 2 times 4 is 8. So I have 8 minus 15. And it's funny because if I don't do this, I'll make a mistake. Okay, negative 7. So I get negative 3x over 4 minus 7/4 equals y. And so this is my linear equation. Okay, so that's the first skill that we're really practicing today, is being able to, from a linear equation, get a parametric, which I'm not going to lie, is kind of silly, and it's when we get to quadratics and circles that becomes more important. But I mean, just the concept we have to practice, and then going from a parametric to a linear, which is a little bit more helpful, because if you have a parametric, sometimes you want to graph it and do stuff like that. Okay, how are you guys doing? Does anybody have any questions? Do you guys see here? I have to zoom out just a little bit. But do you guys see how my original parametric equation and this linear equation are describing the same physical phenomenon, right? These aren't two separate things. It's two ways of looking at the same thing, right? You can think of it in terms of output and input, or you can think as how is X changing with respect to time, and how is Y changing with respect to time. So it might be easier to think of a coordinate system like a field, and this is like, what's the X and Y with respect to time? Like, so someone's running in a field, and you can be like, where are they in terms of X at this time? Where are they in terms of Y in this time? Okay, and you're going to see this is going to be really helpful for classical mechanics. Okay. Now I'm struggling. I'm trying to figure out if I want you guys to practice doing that or not, and I'm deciding not, because we'll practice this a little bit tomorrow, but I do want to focus more on quadratics, because I think quadratics are more important. But let's do one story problem. Okay, because I feel like I did a problem where I was like, okay, how do we get to a parametric? How do we get from parametric to linear? Now let's look at a situation where parametric would make a lot more sense. And you guys are going to look at this again tomorrow. So let's imagine we have a canal, because canals are going to be man-made, right? And in that canal, there is some water going this way. Okay, so the water is flowing. And let's say the water is flowing at a constant rate. Yeah, we can bring in Sharkberg here, because parametrics have to do with vectors. Okay, so let's say we're going, so let's say we have a flow. So let's say water is flowing to the right, and I'm sorry for my students that are directionally challenged, to the right, right? Just remember, if you can make an L, that's your left hand. Okay, so water is flowing to the right at, I don't know, how fast does water flow? 5 miles per hour. I feel like that's pretty fast. Okay, and then let's say we have our shark. I don't know how to draw a shark top down. Okay, so there's my shark, and my shark wants to get to the tasty humans on this side of the canal. Okay, to eat the humans. I mean, because like Sharkberg. Okay, so the shark, or Sharkberg, is swimming straight north, okay, at 7 miles per hour. Okay. Now, we've talked about this in terms of vector, right? So like, well, the last time we did this problem, we're like, let's find the resulting vector. And what we found, and here I'll use blue, right? We know that the water is going this way, Sharkberg's going this way, and then we said, okay, well, we know that Sharkberg is going to be traveling that way, right? And we wrote a vector. We wrote a resultant vector. But what we didn't do is we didn't write an equation. Okay? So what we're going to do is we're going to use parametric equations to easily write an equation. So to do this, we have to have a little bit of understanding of units, right? So 5 miles per hour. So if you times miles per hour times hours, right? So remember when we say 5 miles per hour, what we're really saying is saying 5 miles over hours. So if you multiply that by hours, what happens? You get a distance, right? You guys see how that works, how the units cancel out? So when I go to write my parametric equation, well, in the x direction, I'm going 5 miles per hour, where t is in hours, right? And then in the y direction, right, due north, right, I'm going 7 miles per hour. Okay, now, we're assuming, right, that my coordinate system is located at 0, 0, right? And that's the cool thing about coordinate systems. We can change where they are, and you guys are going to see over the next couple of weeks, right? It's gonna be really frustrating when they don't pick the coordinate system to be 0, 0, because then you're gonna have to move things. It's gonna change your parametric equations. Okay, so does this make sense? This is a parametric equation to describe the location of Sharkberg. Yeah, like that's like hecka cool. So I could be like, after 10 minutes, where's Sharkberg? Okay, pretty cool. Now, what this isn't good at doing, right? I'm not gonna, like, this, to graph this would be tedious because, right, you'd have to, well, and that's not true. Graphing calculators usually have a parametric mode, but you're gonna have to read your instruction manual on how to do that. Okay. So the next thing you might want to do is, okay, I'm starting to get parametrics, and like this describes the location, because maybe all I care is how far away down the river am I from my target, you know what I mean? Or maybe all you care about is how close to the shore I am. You guys see how that gives you so much more power? Like, I don't care about that. And we're gonna see an example of that today when we do quadratics. But if I wanted to get this to a linear, oops, there's an E in there. Okay, then all I have to do is solve. So I would get x over 5 equals t, and y over 7 equals t. So we would get y over 7 equals x over 5. And so you get y equals 7/5 x. So there you go. There is it as a line, which makes sense, right? Because every hour you're going forward 7 and you're going right 5. Isn't that cool? Doesn't that make sense? I feel like if like algebra 1 taught with parametrics, that actually might make math make more sense. But maybe I'm just crazy. It could be I'm just crazy. Okay. Yeah. Well, I mean, of course it's actually good. Come on. Okay, so do you guys see that? Like the slope, right? It was just breaking down. So like, now when we have slope here, right? This is the slope in the x direction, and this is the slope in the y direction, right? So then we start getting like, right? We start getting meta with what slope means. And then when you get to calculus, it's going to be, right, how is the x right? What's the rate of change in the x direction? Because the derivative tells you the change in, right? So that's going to be really important, especially when you get to 3D modeling, right? So think of like a mountainous area with like a valley, right? So if I go this way in the x direction, how am I changing? If I go this way in the x direction, how am I changing? If I'm going this way in the y direction, how am I changing, right? And so this gets really important when you get more variables. All right, cool. So we'll have an example of like this tomorrow, right? So this is like an example of linear parametrics. So now let's take a look at nonlinear parametric. Let's start going down that. Let's go do some quadratics. Okay, so this is where we get into classical mechanics. And one of the things, I know a lot of you guys have taken physics. One of the first things you do in physics is you're like, hey, if I throw a rock or a pen, what happens, right? Or if I fire a cannonball or shoot from a gun, or right, anything, any object, what happens as soon as the force acting on it stops? And that is the only thing acting on the object is gravity, which is wrong. There's also drag, which goes by a quadratic. But your physics teacher lied to you and they have no regrets, okay? Because it's a really good approximation without drag, right? As long as we're assuming things that, like a cannonball that's not too big, or a bullet. But there is drag. And if you guys like watch those really cool History Channel things about snipers, like shooting long distances, wind is a big factor, okay? So what happens is, you get this. So let's say you have some land, you have a cannon, okay, and this is where maybe a little fuse. So what happens is you get this ball shot out. So this ball is going to have, oops, right? It's going to have a vector there, but this vector is going to be broken up into two parts. There's going to be, so if this is vector v, and we talked about this last time with components, there's going to be an x component, and there's going to be a y component. Okay, oops, sorry, a y component, v sub y. Now what's important, in physics, we call this v sub naught. So this is your initial velocity. Okay, your initial velocity, because that initial velocity is going to how you're going to find your initial Vy and your initial Vx. Now, I'm going to be doing a little physics lesson here, but okay, that's kind of the orbital trajectories, but what physics tells us is that an object in motion stays in motion. So it turns out that v sub x always stays the same. So v sub x is always the same. Okay, because there is, now, again, this is technically not true, so I'm lying to you. And if Ingman didn't tell you that he was lying to you, you should tell Ingman that he's a loser, McLoser face, and that Mr. Kraft is better in every way. I'm sure he would really appreciate that. Okay, and then tell him he needs a stamp on his head for lying to you. Okay, so the only thing, right? So I am lying to you, right? So you guys, so when I say Vx is the same, right? We're ignoring drag. How do you spell ignore? Ignore, whatever. Ignore drag. Okay. Yeah, pass the word, tell him. Yeah. The only thing that changes is your Vy. And Vy is 0 here, and then it starts going down, and down, and down. Okay, so it starts high, and then it gets smaller and smaller, and this is to gravity, the force due to gravity. So in feet, right, so the force due to gravity is negative, and we say negative because gravity acts downward, is negative 32 feet per second squared. Okay. Or for the rest of the world, okay. All right. So, hopefully, if you guys have never seen this, welcome. You guys should take physics, right? This is part of classical mechanics. So, what's going here is notice how our vector going through the Vx always stays the same. Okay. Yeah, physics is awesome. I wish I was a physics teacher. Okay. V of y equals 0 at the vertex. And if you don't believe me, take your pen, throw it up in the air, and you'll notice that when your pen reaches the highest point, it briefly stops. Right? So if you want to catch something that's shot really high in the air, you want to catch it at its vertex. So for example, if you shot a bullet straight up in the air and you were able to go up on an air platform and reach out your hand right where the bullet reached its max before coming back down, it would just softly just plop into your hand because it has no y velocity at the peak. That's pretty cool, huh? So weird teaching when no one responds. Yeah, making bombs is really easy when you know physics. All right. So now that we got that out of the way, okay. So really quickly, so if initial velocity is 16 feet per second at an angle of 38 degrees, find v of x and v of y at time equals 0. Okay, so yeah, no, you should stop by Ingman's room and tell him Kraft is throwing down. I hope you guys know that Ingman and I have the same degree and we're both married to social workers. So basically, that makes us the same and same degree from same university, and so that just makes me a better, younger Ingman. No, greater. You're the equals the wrong one. If I'm gonna start something, then you gotta use fighting words. Okay. So what this means, right, is our initial velocity is 16 feet per second, and we want to find Vx, and we want to find Vy, and our angle is 38 degrees, right? So this is trig. So, ooh, I've been trying to kill Ingman to take his job for years, and he still hasn't died yet. So, if I told you I don't actually like teaching math and I would rather be teaching physics, would that be weird? All right, so, right, so this is just trig, right? So this is going to be 16 cosine of 38 degrees, and v of y is going to be 16 sine of 38 degrees. Okay. So I'm just showing you how trig comes into this because I'm kind of doing a crash course in physics. I don't think bees phase him anymore. If I really wanted to get to him, right? If I really wanted to get to him, I'd just poison his tea. He's a tea drinker like I am. All right. So let's get into some real stuff now. Okay. So I'm going to do a little storytelling. So let's say a professional football kicker. Okay, so here's maybe field goal. Sorry, my field goal here kind of sucked. There. Okay, and then this is my professional kicker. You can tell my football is really good. I play a lot of soccer. Okay, there's my football. Now, he or she is going to kick the football. Right? It's going to follow quadratic. So the initial velocity, so in physics we call that V naught, that means initial, equals 29 yards per second at an angle of 68 degrees. Okay. Suppose the kick returner, catches the ball five seconds later. Okay, so that's what we know. We know that it has an initial velocity of 29 yards per second at an angle of 68 degrees. Suppose that the kick returner, right? So this is the kick returner. Okay, so the kick returner is going to catch it in 5 seconds. Okay. So we have some questions that we might answer now. So the first one is going to be, how far did the ball travel horizontally? Right? Because that's all they care about in football. Okay, so how far did the ball travel horizontally? Okay. Okay, how far did it travel horizontally? And when caught, how high off the ground was it? Okay, so 2 questions. I know I started a sentence with and, so tell your English teachers and they can murder me later. Okay, so I didn't even capitalize and. That's how ashamed I was. So again, this is going to be a job for parametrics, right? A quadratic isn't going to tell us this information without calculus, right? So calculus is we could find this information, but parametrics is going to, it's just so much easier to do because we can break it into a horizontal component and we can break it into a vertical component with respects to time. Okay, so how do we do that? Well, right off the bat, we already know that x is going to be my initial velocity, right? Cosine of theta times time. And we know that my y is going to be my initial velocity times sine of theta times time. Now, again, where am I getting sine and cosine? Remember, when I'm doing this, I'm breaking this up using right triangle trig, right? So my x is cosine, my y is sine. Do you guys see that? So it's my initial velocity times cosine and sine. I hope that makes sense. I hope I'm, like, I had to do a quick little reminder lesson of that. Okay, so then that means my x is going to be 29 yards per second times cosine of 68 degrees times t, and my y is going to be 29 yards per second sine of 68 degrees times t. Oops. Now, so this is my initial. Now, what happens here, and I'm just kind of walking you guys through this, what happens here is that this is my initial velocity, but then only one force happens, and that's in the y direction. And so we're going to subtract 1/2 32 t squared. So this right here, and I know that I don't have time to teach a lot of physics, but this right here is gravity. Okay, and if we had more time and I was in class, I would show you where this comes from. Okay, I would, we would break it down. If you're in physics, you already know where this comes from. And sorry for those of you guys who haven't taken physics. Okay. So all we have to do then is set t equal to and solve for x and y. Okay, so all we have to do is set t equal to 5 seconds and then solve for x and y. Okay, so again, today, I know I kind of just threw you guys into quadratics and trial by fire, right? Like, you just kind of have to take my word that these equations work, right? But the whole point is why parametrics, and I hope that with quadratics this makes much more sense, right? This isn't information that we can answer with the traditional quadratic formula, right? With the quadratic formula, we can figure out, okay, when did it leave the ground and when does it hit the ground, right? But I can't find when is it caught, all right, or how far did the ball travel. I mean, I guess you could do that if you approximated from the ground to the ground, right? Okay. So, does anybody have questions about this so far? You guys are feeling good? Well, here, let's go ahead and solve this really quickly. So the x here, I'm going to have 29 cosine of 68. And we're going to have a worksheet tomorrow, guys, that we're going to work on in class. Okay. And then times 5. So my distance, or I should say horizontal, equals 54.318 yards. And the height, so let's do this. I'm going to 29 sine 68. So this is my initial, right? That's my initial, times 5 minus 0.5 times 32 and then times 5 squared. And I get, nope, did something wrong. What did I do wrong? What did I do wrong? What did I do wrong? 29 sine of 68 times 5. I wonder if it didn't like where I put the 5. That's probably what it did. So 5 times 29 sine of 68. Oh, that's why, because I'm using different numbers than the book. Oh, whatever. But this answer didn't make sense. 29 sine of 68 minus... Oh, that's what happened. I didn't pick a high enough initial velocity. Okay, well, I'm going to own up to that. So I'm going to say my answer is negative 265 yards. So this person is in the Earth's crust. So this person is in the Earth's crust when they catch it. But the reason why is that this initial speed is way too low. So that basically means that that I'm an idiot and I should just use the numbers that the book uses. All right, so before you guys leave, I just want to give you guys a heads up of what we're gonna do tomorrow and what we're gonna do from there. So tomorrow I have a worksheet that we're gonna work on. Wait, don't leave yet. I just want to make sure you guys understand this. So you guys took your final. Okay, so you took your final. Make sure what's gonna happen. I know some of you guys were concerned about your grade. So what I'm going to do is the work that we're doing here, I'm gonna make it worth points, but I'm not gonna make it worth 10 points. So I'm gonna make it worth, like, for example, let's say you have a B minus, this will bump you up to a B. Or if you're at a B plus, it could bump you up to an A. So it's gonna be enough points to where if you're sitting, it's gonna bump you up like a quarter grade, okay? And we're gonna be working on that. So tomorrow we're gonna be working on linear and quadratic. And then the day after that, we're gonna do circles. So we'll spend 2 days on circles. And then I have some really big challenge problems that I'll have that you guys can work on as well, okay? So that's it, guys. Take care. I will see you tomorrow. You guys can pack up, and yeah, we'll make it chill these last few days. Bye, everybody.